All right. Yeah, so let's maybe start off with like quick updates from folks. Thibaut, would you like to go first?
Hello everyone, it's been a while.
Hey.
Took some days off, so no major update in the last few days. I got the revision from the TKC case study paper, so I'm gonna work on that soon. Mostly positive, but like question about the approach and everything like that. So we'll see how that goes.
Excellent. Sagi.
Yeah, actually I worked quite a bit, like bit of different things. So I'm getting a lot of like a request from other people these days.
Yeah.
So yeah, it's like Anyway, so I helped a little bit the CSM guys who worked on the IP. So like I implemented the complex conductivity model in the frequency domain code. Anyway, so he ran it, and that matches with analytics. So I guess he's good to go. So
Nice.
I think he said Andre's student, I guess. So anyway, that was good. And some of the Stanford crews are working on time-lapse inversion. So we got 2 airborne EM surveys flown in 2-year separation, particularly for the seawater intrusion. So yeah, we're ready to run the time-lapse inversion, I guess. So it's gonna run.
And that's a 1D airborne EM?
Yeah. Here it's all 1D, no 3D. Although we do 3D simulation. So and I'm helping John to invert the Bona Vista data. So I think they got both DCIP and airborne data, and seems like both of them are showing the IP effects. So yeah, my portion is like revisiting what John did and invert DC and IP and see if there's a correlation between airborne and IP, I guess. So yeah, it's like lots of things going on. I'm trying to manage things, but so my plate's getting full.
If I can add a point on the airborne IP, I don't know if Dom already made that point. So like late January, there was the a roundup conference in Vancouver, and we went to see the talk from Andreas Viesoli. That was really cool.
Yeah.
And like for me, the message he had, like he had a lot of message, but one that really struck me was that his personal estimation was that at least 50% of airborne EM soundings were influenced by IP effects. Like he was saying, like majority of the EM soundings had some IP effect in them. Like not always going into the negative, but he was thinking that it was probably something that was like much more common than we thought.
Yeah. It depends where you go.
Yeah.
Yeah, it's like, if you go to like a Canada or somewhere in northern Canada where like your background is very resistant, he's correct. Yeah, there could be lots of IP effects, but if you're living in a California, very conductive, then there's actually no IP effect here. So I mean, like it depends upon the context and where you go. I mean, like his context was actually showing the airborne IP, so yeah, right. But, depends.
Cool. Thanks. John.
I got quite a bit of headway on the MT. I saw what you guys were doing with storing the factorizations with the fields on the frequency domain side, I think. So I've applied that and then dashed the fields as well for the MT. And then I've got JVEC and JTVEC. I was playing around with that to get it parallelized. And using the test models, I sped up the JVEC from 90 seconds to about 45 seconds, so almost about JTVEC is still a little slow, and I don't know. I think it's because when I run the fields, JTVEC needs to store A transpose inverse, so I'm storing both of them. So they cost a lot to run, but they're quicker, but they cost quite a bit. And I was thinking about maybe writing them to ZAR, but I don't know, by the time you're reading and writing them over again, maybe
Well,
you're not going to get it.
that matrix should be same. So you're solving symmetric matrix. So A and A transpose. I'm pretty sure like
Oh, really?
there are probably like couple of cases, I guess. I'm not sure, but like a transpose and A should be same. It's
Yeah.
like,
Oh, yeah. I'll run a few tests on that then. Because yeah, then I'm just saving both things, and it's just doubling up the RAM. Yeah, that could be.
So you're saving a factorization for each frequency?
Yeah, for each frequency, yeah. Yeah, right now it's just storing it right to RAM. So it, yeah, like I've got a test here that I'm running on something on our simulation with like 16 frequencies, and it used to run, well, it was with the slower version runs at about 10 gigs. Now it's about 50 to 60 gigs.
Yeah, it should. I mean, at least I need to double check the current MT implementation, but everything that we do with the frequency domain code, we're always working with the symmetric A.
Oh. Okay.
And we should be for the MT code as well.
I think, yeah, I was looking at it, and I think MT is symmetric as well.
Yeah.
I guess that comes back to my other point that I brought up last week, is that we should provide a few little hints about things and like a little bit of documentation. Be like, oh, this A matrix is symmetric. This is SPD. This is Hermitian. This is, yeah.
Yeah, if someone could maybe take a look just to confirm. I can try to.
It should be. I'll definitely double check, but like I'm 98% sure that the current implementation would be.
well, like John, you can check A, like try A and A transpose and see if that's like the same, right?
Yeah. Yeah. Right, sorry.
Yeah.
No, sorry. It should be a matrix, but
Yeah.
So
I just sorry, Joe.
how big of a problem are you testing this on?
This is about it's fairly large, 16 frequencies, about 441 stations. It's only 52,000 cells, but I guess semi-large.
So the mesh itself is not that large.
Yeah, the mesh itself is pretty small, yeah. But yeah, it's the amount of frequencies, I think that's really, yeah.
Well, so what I've seen is with the MT stuff, if the mesh does get larger than that, like it tends to take up a lot more memory requirements as it's going on.
Okay.
Because it's not solving on cells, it's solving on faces, right?
Okay, yeah, it's the elements, right? Or the number of elements?
It's solving for the field of faces, or edges. So basically like triple the amount of cells. Or like almost 8 times the amount of cells that it needs to solve. So
okay, that makes
I mean, if we start storing at every frequency, yeah, it's going to certainly speed up those things. But I mean, when you start running like even larger models, it takes like 100 gigabytes to do this factorization. Well,
so it's probably just better to just take the time instead of.
I mean, it might be an option, but this is one of the things where we should really. I mean, it's kind of hard to optimize around some of these solvers, but at least we should provide an interface to PyMat solver that would allow you to not have to do some of the backend steps. So we could take advantage of things like, with Paradiso, you can do a step that just redoes the numerical side of it, numerical factorization, like doesn't have to recompute the symbolic factorization every time, which was something we should be taking into account, like most of these times, right? Because the matrices are dependent on the mesh. We're not really changing the mesh, right?
Yeah.
So we should probably provide an interface to PyMat solver that does that kind of thing. And that would save a little bit of time. I mean, the numerical factorization still does take a decent amount of time, but it cuts a little, one step out at least. It gets repeated every single time.
Okay. Yeah, no, that sounds nice.
Just thoughts. I mean, these are things I think about when I saw people doing that, and I just kind of,
Yeah, fair enough. Yeah, I was kind of just going for the speed right away.
Yeah, the fact. Yeah. I mean, it's nice when you're doing that, and you get like a, when you start running into things, where it's like, okay, well, the Paradiso solver, okay, that only works on a single node, right? It doesn't. Paradiso doesn't solve on MPI systems. Like, you can't take advantage of MPI stuff, so you're always going to be limited to the amount of memory you have on one node when you're using Paradiso.
You're using one node. Oh, okay, fair enough.
Yeah, just things. Anyway.
Sean, any other updates or?
That's about it.
Okay. Cool. Joe, would you like to take the floor?
Sure. I've been working on some one project that I've been using for this kind of leftover stuff from mines. It's a forward modeling project, so it's been using NT IP modeling. Just kind of going through and double checking that I understand how to use everything and making sure I know how to run it correctly and make sure everything's going on, and then optimizing, finding little parts to optimize and pay attention to certain parts. And like what I'm talking about like a few minutes ago, I realized like, oh, it's actually can get to be a pretty big system. The size of the model domain we were working on was about 25 kilometers by 30 kilometers. And just breaking that up into something, and the model is pretty variable across the whole domain. And just breaking that up into things that are like, even like a 200-meter discretization, which there's certainly things that's getting a lot about big for the size of the anomalies that are in this model. Even that is like, okay, it's 100 meters or 100 by 120 or something each dimension, and that trying to do an MT3D modeling on that was just took about 300 gigabytes of RAM. So it was like, it tends to blow up pretty quickly. So that's why I was kind of like thinking about that. The IP modeling kind of got me thinking, is there a way that we can have like an electric dipole source for the static field solution?
What do you mean? Because we can.
Right now, it's all current sources, right? For the static simulations.
The static simulations, you can treat them as like point charges.
Right.
Right, because we don't need, like, so for a DC or IP, we don't need the connectivity between the two locations, between your two electrode locations. So effectively, like with the cell-centered discretization, we're just treating the sources like a charge at the cell center, and with the nodal, we then just like average to the.
Yeah, no, I understand that part of it, but it's just kind of like, so those are essentially like point current sources, right? Point charge sources. So I'm just kind of curious if there's a way, like, because I mean, if we have a dipole source, I'm just kind of curious if there's a way we could like not have to have basically
it'll cancel out, Joe. So if you define the current source as a current, which is a vector, then you take the divergence, then you're left with like plus or minus
right
at the endpoint. So in between, it's zero. So you could like you could actually use the line current source in what we're using in the EM code. And by just taking the like a divergence, you can actually effectively get at the point source as well. But not needed, but you can.
No, I understand. I just kind of think if there's a way, because basically it's like it kind of requires pretty small discretization around the current electrodes, right?
Well, I mean, if you have like a dipole source, I mean, usually what we do is have like 4 cells in between. You could test what
Yeah.
happens if you have basically, you know, a positive in one cell and a negative in the next one. And that's basically as close as what we're going to be able to do to a like an infinitesimal dipole.
Yeah.
Like, are you worrying about the accuracy, Joe? Is that?
Yeah, basically I'm worried about that. I'm just kind of thinking.
There are a couple tricks that you can use either analytic solutions rather than discretizing it. I mean, there's some tricks what people tried, and I think that some of the UBC code actually use that trick, that types of trick, I guess.
Would that be like you just do a primary secondary with that cell?
Sort of, but you also got the topography, so you need to take account like when you got the topography as well. So it's not like just a half space solution, but you need to use this emitter solution and to figure out what's the sort of the topographic effects. But or like
you're talking just like using that to get somewhat accurate boundary conditions and source.
Yeah. Or you could you could solve the DC equation for the right hand side. Suppose you know that this is an analytic solution. You can solve for the right hand side.
Yeah, I know, I've looked at that before. Yeah.
So I mean, there are a couple of tricks. I don't know. I mean, like depends. Like if you really need a really good accuracy, then maybe. But like typical or 5% DC data seems pretty fine with what we have now. That's what my conclusion was.
Okay. Just thinking.
And how are you feeling about the simulation stuff? Like what? Yeah.
Right. So okay, for that stuff, I've been going through like most of the pull requests and just trying to like see where things are at, and it feels like there's some basically dead pull requests that are either just kind of like, okay, well, somebody did this in another one the same way. Somebody did like open this pull request and then did nothing with it.
Yeah.
So I mean, I've been working through the other stuff. I mean, it's little bits and pieces here and there. Basically, what I really need to get done is I want to get the read figured out. As far as the simulation stuff, not many people have chimed in on that issue that I posted on SimPEG.
Sorry, you cut out, at least on my end, on the
on renaming.
Ah, I see.
Yeah, not many people have chimed in on the issue that I put up on the SimPEG repository. Maybe I should put a link in discourse about that, or a link in Slack, ask people to say things. As far as the standard deviation thing, people have also not, like only a couple people responded to that.
Would you mind actually posting those? I think both in Slack and in Discord, because I think we talked about it at the last meeting, but I didn't chime in on the issue, and I'm happy to take some time to document my thoughts there.
Okay.
Yeah, but I need a poke.
Sure.
Thanks, Joe.
At this point, I'm trying to, as far as the standard deviation, like the names of things, I'm kind of thinking, okay, we have a noise floor, so I'm thinking a noise ratio. Kind of seems like it's pretty clear what it is, and I don't know.
Yeah, that's getting closer.
Yeah, it's kind of like I like that it's kind of like symmetric with noise floor. I don't know.
Was everyone else who's in the call right now a part of that conversation? Because we talked about.
I talked a little bit with Thibaut before he left about that, I think.
Yep.
And John and Sagi, were you both in that? We were talking about basically how like the term standard deviation that we're using when we construct the noise isn't actually standard deviation. It's like it's a percent error, except it's not a percent, it's a ratio. So what should we call that thing? Was the question.
I think with the percent error thing, it might be just easier just to have a check if someone puts it in as a point, or as in like say 50% or something like that. It kind of seems hard to what do you name it? I don't know. The name is just, it's, if you call it a percent, you're going to get two different thoughts on it, of course. And I think it just might be easier just to do a check within the code to see.
What was the thoughts for relative error? Was that on the table, or was that dismissed?
That wasn't raised in my view. So that might have been an issue, but I didn't. Yeah, I mean, that something like that could work.
Yeah, relative error actually sounds nice.
Mm-hmm.
I'd vote for that.
Yeah, I think it's clear it's relative, but like after that in the documentation, we can say what we expect. I'm still happy with the ratio, like putting 0.1 for 10%, like not assuming it's a percentage already.
Yeah, it just seemed kind of hard to do some sort of checks for that. Okay, what do you do? Like if it's greater than 1, it's a percent. It's less than 1, it's a ratio.
Yeah, that's the point.
Yeah, but I mean, I think if we do, to Thibaut's point, if we do something like relative error or noise ratio, I think with either one of those, we can basically then just do like a validation when it's input. And if you have entries that are larger than 1, we throw a warning at you, I guess. Because there might be some where you actually want a huge error, because instead of like removing that data point, you're just like, whatever, I'll just set the error to 400%. And that's fine. So yeah, we don't necessarily, I think, want to like have that be a something that stops the code running, but it should be a pretty like flashy red error or red warning.
Did you mean to do?
I'm sure you want to be doing this, yeah. Okay, yeah, I am liking relative error or noise ratio. I'll be curious to hear Doug's thoughts on this too, because I know, like, with his experience, I'm sure he's through some of these things too. Sagi, do you have a strong gut reaction to any of those?
No. As long as like we're consistent, I'm good.
Sounds good. Perfect. Okay, I can give a quick update on what I've been up to. Yeah, I've been fielding a lot more emails recently, which is kind of cool. That means people are poking around in SimPEG. But for me, that also sort of feels like we should push to try and get the simulation stuff out sooner than later. In part two, because it's like so much of an improvement on the documentation and the number of examples and things like that we have. Yeah, so like even if there's things that we want to optimize, I think if we are like as good as we are currently, and the naming and stuff is now consistent, then we can get that moving. So I'll chime in on some of the naming issues, and then I guess I think Doug and Dev are back next week, so we might actually
be their last week there.
Yeah, so then we can maybe round out this conversation with them, and then sort of like make some decisions and get this done. And then the other thing I've been working on is the machine learning side of things for UXO. And so maybe in like 2 weeks time, I'd be happy to show some of the stuff that I've been doing. All my notebooks are online, but they're right now very challenging to digest because it's very much a stream of consciousness. But if you're curious to take a look, you're more than welcome to. I will drop the link in there. And yeah, so we've been working with some of the folks at Black Tusk to get some data, and also to work with just their simulation engine, because they've got all of the ordnance objects and sort of their decay characteristics, and then the approximate dipole modeling for their system and things like that all set up. So.
Right. Are you using Silk code to generate the synthetic data? Well, like like are you using their field data to generate the machine learning, or what's your data? What's your training data?
Yeah, so right now I'm looking primarily, I mean, they sent me some field data, so I will be using some of that. But for now, what I'm doing is generating synthetic data using their forward modeling code. It's basically just, it's an approximate physics model where we treat an ordnance object with 3 different axes of, basically, like they're three orthogonal dipoles, each with a characteristic decay curve. So you're basically solving like an electrostatic the magnetic problem at every step. So we're not considering sort of background geology or things like that. And so one thing that actually would be super interesting is to go in and like look at down the line, maybe actually generating some EM data where we do run a simulation with perhaps the SIL code or something like that, and compare and see if like by augmenting this approximate physics model with a handful of sort of full-blown physics simulations, do we get a more robust model or something like that? Yeah, but for now I'm just sticking with like the bare bones simple let's treat it like that.
But are you like doing a decay by decay? So your input is basically decay, and then answer is whether that's UXO or not, or something like that?
So inputting, it's kind of an interesting system. So let me see if I can pull up some slides just to show you kind of what it looks like. Can you see that?
Yeah.
Okay. So the system is interesting. So this is basically what it looks like, and you would go this way. You can see my mouse, right?
Yeah.
Okay. So you would move basically in and out of the page. There's 5 different transmitters. So those are big squares. And then there are 11 different 3-component receivers. So it's a very well-structured data set. So basically, like transmitter 1 is going to fire, all the receivers listen, transmitter 2, 3, 4, 5. And then basically you're just rolling along with a system that looks kind of like a lawnmower. I don't have a picture in here. It looks like a giant lawnmower. It's basically like 2 meters wide and then 1 meter across.
Right.
And so then what I'm inputting, I don't actually know if I have, yeah, I do have a data image. So what, I'll just zoom in on this. So this is like some of the data that you're looking at for just a single transmitter. So this is one transmitter over a target that's basically centered at 1 meter-ish. And so with what we have is basically 165 input channels at each location, if that makes sense, or approximately each location within a given like pretty small window, because it moves along, like we're not sort of sitting and firing a transmitter. But basically you get like 5 transmitters times 11 receivers times 3 components is your input channels. And so then from that, what we're trying to do is basically say, okay, what is this a UXO or not? And potentially also even what kind of UXO is it? Like, can we distinguish between a small ISO and something that's like 150 millimeters, or something that's big? And we should be able to.
Do you need to locate the like in the horizontal location as well? Because like it's a fairly large loop, let's say 2 meter by 1 meter. You still need to locate horizontally and also the vertical.
So that would be a next step. Right now, it's basically just like if we have an image of data, can we just identify like this anomaly is due to this type of object? And then from there, if you already know what type of object it is, then that can basically be fixed in the inversion if you want. Or like you're starting from basically you're starting from a place that's much closer than you would if you don't know anything about it.
Oh, that's cool.
So yeah.
That's pretty cool.
So that,
Hey, Lindsay, I looked at one of your notebooks there. You're using PyTorch, is it?
yeah.
Oh, nice. How do you like it?
I really like it. I've played around both with PyTorch and with TensorFlow.
Yeah.
And for me, the TensorFlow API, I just could not get my head wrapped around it. I don't understand it. Whereas with PyTorch, it felt way more natural. So I feel like I roughly know what I'm doing with that.
Okay, yeah, it does look, my problem isn't quite as involved as yours, but yeah, I've had a pretty good time with TensorFlow, but I did play with PyTorch before, and you're right, that the API is really nice with it. It's
Yeah, I mean,
Yeah.
I played around with different, oh, go ahead, Thibaut.
Yeah, I was gonna say I played a bit with both too, and I liked PyTorch 2 better because also TensorFlow I found was like very, like it does well what it's supposed to do, but if you want to implement something new or like yeah, like just play around with it, it's much harder to modify. Like while PyTorch is much more flexible.
Can I show one of mine, actually?
Absolutely, absolutely. One just quick follow-up comment on Thibaut's comment. I think that TensorFlow 2.0, which came out maybe a month or two ago, I think that API is much closer to the PyTorch API.
Okay.
So I think that that's perhaps gotten a bit more aligned.
They're
John.
allowed to share. Oh.
It should be in the bottom. If you mouse over Zoom, there's like a green.
Yeah. Oh, it just keeps giving me open systems. Oh, geez. Oh, where it is. Okay. I gotta put my map here. Sorry. Okay. Let's try that. Is that working?
Yes.
Oh, okay. Yeah, so yeah, I'm just using the TensorFlow right now. This is just one of my first little training sets. I've actually found that I'm going to go to the actual periods of this time signal. So what I'm doing here is I'm implementing machine learning so that we can look at all, because we got so much time series coming in. Some nodes are disconnected and halfway through, all that kind of problem. So yeah, I've just given it kind of a test data set as an example here. So yeah, it's a little small, but so we got things like tellurics happening, contact, like bad contacts, just bad data that's disconnected. Say a current electrode that's drying up and it's varying the VPs. Yeah, but just using a whole time series as that. What am I implementing here? I just have 2 layers, just like a softmax, and then just I can't remember what the ReLU is, but yeah, I was just playing around an example to go off of it. So just, I think this one only has like 163 samples, and I get about an accuracy of 73% by the end. And it does actually do pretty good. Like right here, I give it that time series and it sees that, oh yeah, that's a timing issue. So
that's really cool.
Yeah, it's actually quite successful. Yeah, grab another one and then it, yeah.
Have you played around at all with convolutions for this? Have you played around at all with convolutions?
Not quite. I've been playing around with it on the new implementation, but yeah, didn't get really too far yet.
Yeah, fair enough. Because I would expect, like, I mean, because convolutions, in some sense, you can almost think of it like you're basically looking at some filter or derivatives of your data. So I would expect on something like this that should train reasonably well.
Okay.
Yeah, so might be worth playing around with. But that's a cool example. How are you generating the data? Are those field data or are you?
All field data, yeah. I'm just going through time series by time series. So yeah, it's kind of painstaking, but it's starting to pay off a bit. So I'm kind of stoked on that.
That's awesome.
The only thing I find is also using different different transmitters. Like the GDD's got like a spike usually when it tends to turn on. So when I'm trying to train it to spot EM spikes, it sometimes mistakes a good time series because of the transmitter. Whereas if you use our transmitter that has a nice turn on, I can actually train it to identify that stuff pretty well.
Super cool.
Yeah. That's a little side thing I've been doing.
Oh, well, thanks for sharing, John. That's really cool.
Well, once you figure it out, it'll automate your work, right? So you don't have to work. Ask your boss, oh, give me your money. I got a code. Oh, you don't have to actually say that. You got a code.
Yeah.
Yeah.
Just go tell you
that. I mean, keep saying, "Oh, I'm so busy."
Yeah, good point. Well, ultimately, we're doing it so that there's more time for inversion.
Excellent. Cool. Yeah, any other items people want to bring up, chat about? Yeah.
John, I was curious, like, where were you for parallelizing DC code? So, like, I know Dom and you worked on using Dask to parallelize the sensitivity computation and storing it with jar. And okay, is that it? Or-
Just the fields and for the sensitivities, yeah, so that we can do the sensitivity depth weighting.
And then did you ended up doing like decomposing like for each, let's say each line, that types of stuff?
Yeah, we were pretty much storing the sub matrix of the giant sensitivity. Bizarre.
No, I was asking like rather than generating entire domain, so you can generate each mesh for each line, for instance.
Oh, on the tiled stuff. Sorry.
Yeah.
Oh, yeah. We kind of felt. I think Dom took it the first step, and we got it to the line, like just doing some examples by line. But that's as far as I know that we got, because I got switched over to some MT stuff.
Okay. And one thing that when I was looking at your IP notebook, when you're setting the uncertainty, you're basically setting the percentage and floor. Is that what what you're used to doing?
Percentage of so a floor, or sorry, I don't.
For the IP data, for the IP data, like it's a voltage.
Yeah.
So are you setting percentage plus floor?
Yeah.
Is that what Charlotte used for her inversion as well?
I don't know, because I do calculate like an error using the full stuff. Actually, hold on, Charlotte. Hold on, sorry.
That's handy. She's in the same room.
For that inversion of Bona Vista, did you use percent plus floor for the error IP?
That's right.
Oh.
No, sorry.
Or did you use the col? Okay, so we use the col error, an error derived from fitting those col curves.
What I usually do is use the DC data, it's like a just like a 1 millivolt, you multiply 1 e minus 3 to the DC data, and I use that. So effectively, it's like an apparent chargeability. So what you're looking is an apparent chargeability. You convert that into the voltage data, but what you care is apparent chargeability. So I don't really care like small apparent chargeability. So anyway,
Okay.
just curious, what's the practice?
The floor wouldn't really take care of it, or
so you're still inverting voltage, but what we care mostly is large apparent chargeability.
Yeah.
So probably best if you can invert the apparent chargeability. We don't have that. I think we do have the functionality, but anyway, you're inverting for voltage data. So what I'm doing, I just set the uncertainty as a DC data.
Oh, okay.
So and then your data is a millivolt per volt. So you just multiply 1 e minus 3 to that, and then it's kind of effectively you're inverting for apparent chargeability. But anyway, I was just kind of curious what we
were aiming for was just I guess getting a sense of the error on how well that curve is, and I guess essentially trying to relate that to how good that chargeability would be by how the curve is.
Yeah, and my feeling is, my experience, if you just invert for voltage data, it's hard to fit the data.
Okay.
So I think that's what I was seeing in your notebook. Like your data fit is not good, right? Like your chi factor is way above of the target misfit.
That one? Oh, okay. Yeah.
Anyway, yeah, just kind of curious what you guys are doing. Yeah.
But I think in the notebook, I think I was just using just a percent, like a standard.
Yes, you did. Yes, you did. So that was the reason why.
Okay, I see. All right. Okay.
One other question I had on the MT side of things is the Octree mesh actually working with the MT code right now?
No.
Yeah, I didn't think so.
Basically, the reason behind that is that there's a assumption that it's a primary secondary formulation of it. The primary is on a 1D sound 1D structure. So
Oh, I see. I see. Got it. Yeah.
it's kind of like it. Basically, I think what we might have to do is just do 1D on the finest tree mesh in the Z direction.
I think it's
know.
worthwhile to later, like just change the formulation rather than using the secondary field formulation and just like set the boundary condition at the boundary. That's, yeah. Other way is not like, yeah, it's not.
No, I agree. Yeah.
Yeah, I mean, I think we could easily keep the primary secondary, but try and use a boundary condition as the...
Yeah, I saw, Joe, it seems like there's all the utilities that you can extract all the boundary faces and edges and stuff. So, I mean, it seems like we're almost ready. So I just need to have a motivation.
I definitely have them. Okay, I definitely have them. I mean, they should work for tree mesh. I mean, they do work for tree mesh. Let's at least find the locations of them. We just need to go through and look at some of the spots where we're making assumptions that it, like, even if we don't realize it, but there are a few spots in there where we're just making an assumption that it's like, oh, it's gonna be a, you know, some sort of structured tensor mesh type of thing. Just little things, I think.
Yeah.
But yeah, we should definitely do it into a way that's a little bit more mesh independent.
Any other questions, discussion topics before we...
Oh, I submitted the well paper. And
yeah?
Thanks, Joe. So I used the Octree code, and I think it was Dom wrote another wrapper, and both like Joe. So that was very helpful. So like I discretized the power lines and solved like EM problem. And yeah, that was actually, we used that for like AEM survey design. So anyway, so that was...
Yeah, the tree mesh stuff works really well when you can use it.
Yeah,
so a lot of time.
So thank you very much. I acknowledge.
That's awesome.
Well, thanks, Lindsay, as well, the KC. So exactly use your code.
Excellent. Well, perfect.
Yeah, actually, I don't know if you mentioned it, Lindsay, but so yeah, Lindsay and we submitted a paper for joint inversion in SimPEG too. So we submitted to JGI like just at the end of January. So we hope to read about it in a few months.
Hey, wow, things are moving.
Exactly. And Thibaut, actually, have you had a chance to post it on the archive?
No, I did not.
Okay. Is that something you would be game to do?
We could, yeah.
Okay. That actually would be awesome, because then we can sort of like, you know, get the paper out into the world a little bit. Yeah. Have you done that before?
No, I never done that before. So probably we can like chat on Slack just to iron out like the few details there might be. But yeah, otherwise too, like, I mean, there is a repository now also in the SimPEG research. Like I didn't set up a binder because the examples were fairly big. Like those examples date back before the tree mesh. So I was still using a big tensor mesh, but I just kept it. But at least the scripts and notebooks are online, just not on binders.
Excellent. All right. Well, I'll see you all next week. Thanks for coming.
See you.